third page of Chandrasekhar. Chandrasekhar book is this way, but radiation transfer is Chandrasekhar. Okay. It's an amazing book, but that is not required for. That radiation transfer is also applicable for stars, black holes, everywhere. For us, for atmospheric science per se, broadband is sufficient. You don't require line. But if you are an inversion fellow, like for example satellite meteorology, you want to derive, invert certain places, you may have to go for line. Line becomes complex. Line is not. Line radiation transfer is involved. Band radiation transfer is lesser. Band means instead of taking finer lines, you will be taking a band. Band is not much affected by little bit perturbations, whereas line is much. Line is significantly affected. For example, water vapor concentration. We'll come across, absorption coefficient and cross section. Cross section is by one molecule or one mole. You can divide whatever the per mole or per molecule that you can determine. Suppose you are taking per particle or per molecule. That is cross section. So you can simply multiply by the number to get coefficient. Coefficient is cross section into that number. But that is in band. In line, it will not work. Because line, there will be an absorption line like this. If the species increases or the flux increases, it will not be uniformly going up, but rather it will be populating in the center in the beginning, and side lobe will be minimum. And as the flux increases, this population in the center will decrease, and side lobe will increase. So you have to really know line by line. But most of the people are not using that because that is required for deriving multiple species. For example, if you want to derive water vapor and all, you can do, but there are some species which you want to derive, you have to line. That's an expert job. Actually, we are looking for an RT, line by line RT fellow in SPL. Beware. If somebody is an expert, we would have straight away recruited, but nobody is there. That is such a rare thing because they have a lot of other options also. RT, line by line RT, from astronomy to any field you get. Anyway, we'll start again. So, I will. Anybody talked about atmospheric radiation? I think Satyamurthy might have covered a little bit. Full extent, because in that case I can go faster. Or what you do is you stop me. I will go a little bit faster, and if that is not explained, then I will explain. All right. Why I put radiation, circulation, and clouds is because primarily radiation is the fellow who regulates the energetics, and that energetics regulates circulation, and circulation regulates clouds, and then it feeds back. Clouds will regulate radiation, and radiation will do circulation, like that. The science of whatever we do is was well known. In fact, in much better clarity to ages, through ages before. I don't know how many of you have read Mekadu. I also did not read in the beginning. I mean, at your age and all, I did not read. But later on, now, off late I read it very recently. Recently means maybe a few months ago. Full spectrum of monsoon circulation is there. Okay. What that fellow tells is, he is telling to the cloud, he is sending a message that's like the woman, the lady is sitting in northern part of India, and he is from the southeast from India. And then he describes these clouds as coming from the south, taking turn, going through Vindhyas, further turn, and then go to India. That line is, learn first, O cloud, the road thou you must go. Then hear my message, here thou speedily. Here means before. Before the mountains rise and rivers flow, that he is telling the location where it is. When thou art weary, means art means art. When you are weary, on the mountains stay, means you stay in the mountains. And when exhausted, drink the river's driven spring. This is nothing but evaporation. And see, evaporation leads to cloudiness. This is a poetic thing, Sanskrit translated in English. Okay, if I read the full thing, it's an amazing thing. Actually, I did it in one sitting. I'm not a persistent reader. I cannot read. I have an attention disorder. I cannot simply sit for 2-3 hours in a book. I take back and this I read in one sitting. To that extent, it is perfect. So you cannot change a word in that. Only thing is this English cannot be, very proper. So the English translation I took it from somewhere. That fellow had all the, the word's meaning. If you just put your cursor on that, the word meaning. So it is very easy to understand. If you read the full extent, he is telling. Actually, then he says there's a turn. It comes. That is actually the region of monsoon where wind takes a turn. And he says it is in Ujjain, north of Ujjain. Actually, he is sitting in Ujjain. He talks about the palace and all that. This is slightly more you go north, then turn left. Okay. So that is the way the monsoon circulation goes, and then go to the mountain peaks. So you see, he is a fellow who is in 4th century before Christ. Or I think see, okay. There's no satellites, there's nothing. How do somebody know? Sitting in North India, and the wind is coming from South Oceans. And there is another stanza in that. In Chaitra, the fellow starts in Chaitra. So you see, the monsoon is not reaching here overnight. It takes time. It starts months before, means setting up the mascarena's high. It takes months before that. Then I think somebody might have talked to you about monsoon. Somebody. So monsoon circulation, if you see, it is like that. So these kind of things are very much known to people and it's very poetic. You see, come to Shelley. This is one of the best poems I have seen. I like it very much. On the evolution of a cloud, a convection, and its destruction. See, I am the daughter of earth and water. It's a cloud. The poem name is Cloud. I'm the daughter of earth and water, and the nestling of the sky. I pass through the force of the ocean and shores. I change, but I cannot die. And after the rain, this sentence is so beautiful. And for after the rain, when with the never a stain, it's absolutely clear. The pavilion of heaven is bare, and the winds and sunbeams with their convex gleams build up the blue dome of air. Means nothing is there. I silently laugh at my own cenotaph, and out of the caverns of rain, like a child from the womb, like a ghost from the tomb, I rise and until the again. So this is cycling of a cloud. Correct. And this is only part of it. It's a very good point. You should read. Actually, what I'm trying to tell is much of the things which we discuss, they are known to people even without all these kind of modern gadgets. Or we say modern gadgets advancement. Earlier it was all wrong. No. Actually, they have much better understanding of the systems. And the better thing is they have an integrated system rather than we are looking for piecemeals. Anyway, so I liked this. I thought I should bring to you that science is not just a science. There is philosophy, there is literature, and I don't know how many of us can write to this precise about an evolution of a cloud in so many lines. Okay, when we write, nobody will read. When we say, nobody will listen. Such a poetic thing. Now let us come to the processes in the atmosphere. This is the entire processes that are taking place in the atmosphere as meteorology is concerned. Top you leave adiabatic processes and all. We have winds, temperature, clouds, and humidity. Means water. This is the primary constituent of the atmosphere that drives meteorology. The radiation is controlled by clouds. The condensation is controlling clouds. Humidity controls precipitation and re-evaporation controls again humidity. That is the right reason. And the winds are controlled by friction. Winds are also controlled by diffusion to a minuscule level, especially in the lowest level. And friction is controlled by ground roughness. Yesterday we discussed this. And ground temperature will be feeding to friction through the wind speed changes, means velocity changes. It's non-linear. And ground temperature, ground roughness, snow will feed to sensible heat flux. That is one of the primary energetics of the lower atmosphere. Sensible heat flux means yesterday we discussed hot air going in, taking heat from here and then going to the atmosphere. That is sensible heat flux. And ground humidity and snow and ground temperature together, including roughness, contribute to evaporation, that is latent heat flux. And all these things, humidity coupled together with the winds, decide evaporation along with the atmospheric temperature. So this picture is put it in such a fashion that whatever one parameter is getting affected, whether it is controlled or it is being controlled, is being affected. So basically why I put this picture is to tell you that what are the parameters that we are, primary parameters that we have to look for in the atmosphere, winds, temperature, clouds. Your Navier-Stokes equation you take, that is the most primary thing. Wind is already there. Humidity, you have water vapor continuity equation. Temperature, you have the energetics that is coming in. And clouds control radiation, again energetics. The processes involved, these are the parameters, the processes involved, diffusion, radiation, condensation, precipitation. Controlled by the next layer, that is again the parameters and processes, that is sensible heat flux, evaporation and friction. And at the ground, what is happening? That is ground, temperature, snow, and humidity. I'm not telling you to understand all these things, but just appreciate the complexity of the processes. One parameter controlled by multiple parameters. Each one of those parameters are controlled by the other parameters. So in a modeling work, you have to account for all this. There are some big arrows and some small arrows, which indicates that the big arrows indicate there is a direct, strong relation. Thin arrows indicate there is a relation, but it can be weaker. Means for a shorter time scale, even if you exclude that process, it is okay. But in a longer run, you have to include that process, otherwise your forecast is complicated. Eventually, we have to do all these things for the sake of hydrological cycle for water. Otherwise, we are not bothered about meteorology. Why should we go? Basically, because of the prevailing weather conditions, especially with respect to rain or warm air and things like that. So, the most pivotal thing on Earth is hydrological cycle. Hydrological cycle contains groundwater, water deep inside, snow, ice, oceans, lakes, and air in the atmosphere. I mean, water in the atmosphere, and then coming back. And it is recycled. I will not take much time on this. This figure is a very beautiful figure, but I will not take much time on that because then I think half an hour will be lost. It is worth doing, looking at it. Trendworth 2007 is the paper there at the top. So if you look for Trendworth et al. Hydrological cycle 2007, you will get it. But one thing which I want to stress upon is the quantity given here is in 1000 cubic kilometer for storage and 1000 cubic kilometer per year for exchange. So this arrows indicates exchange. So ocean evaporation accounts for 413,000 cubic kilometer in a year of water getting exchanged. And land precipitation, that is rainfall over the land, accounts for 113,000 cubic kilometer. And ocean precipitation is much larger because most of the rain occurs over the ocean. Okay. And most important thing is the atmosphere contains just 12.7. That unit is again same thing. 1000 cubic kilometer per year. That is so. So you see how little is the amount of water in the atmosphere. But that 12.7 is the main controller for the whole meteorology and exchanges. Water is the energy storehouse. This is a very simple thing. I'm telling it is +2 physics. Water, what is specific latent heat of fusion? It is 334 joule per kilogram. or joule per gram. At 0 degree centigrade. The specific latent heat of vaporization is 2258 kilojoule per kilogram at 100 degree centigrade. What does it mean? It means when ice is melting or ice is getting melted, ice is getting formed. Ice is getting formed means it will take. Ice is getting melted means we are releasing. 334 kilojoule of energy will be released by 1 kilogram. See any other species, hydrogen, oxygen, nitrogen, doesn't reach anywhere. They are among the important species. That too, it happens at very low temperatures. And look at the specific latent heat of evaporation, 2258. This is why water at 100 degrees centigrade and water steam at 100 degrees centigrade, it will cause huge problem in your burners because of that 22. Because when it is converted, 100 degrees centigrade water has some heat in it. When it is converted to steam, again steam is 100 degrees centigrade, it has an additional storage of 20 to 58 kilograms per kilojoule of energy stored in that. The moment your hand is put there, that whole energy is dumped in your hand and it will burn like it. So steam will burn like anything, whereas 100 degrees centigrade water will not do that. Of course, it will cause a burning. It is no way comparable to what it will do for steam. It is because of this. Actually, if you look at the energy transfer and from solid to liquid, that red line, that phase change occurs. The temperature remains the same. As 0 degree centigrade, phase change occurs. That temperature remains the same, but this energy is fully converted. Temperature remains the same. So temperature is not the only factor. Phase of the system is equally important. That's what it means. Then your liquid form, when it is evaporating, temperature remains the same, but the energy storage is significant. This is the most basic aspect of the energetics of one of the most important aspects of the energetics of the energy system. This I just put as a very basic thing. And now let us go to atmospheric radiation. You do know solid angle? If you don't know, there's absolutely no problem. Okay, I'll explain perhaps because some of you may have some problem with respect By the wavelength band only, now I say spectral radiance. What you get in Planck's black body curve, you know Planck's black body wavelength or frequency versus the energy that is liberated. Y-axis is E lambda, spectral radiance. Unit is watt per meter square, first radian. Okay. X-axis is the wavelength or frequency. You can convert, and then the shape will change. That's all. So in that case, we will say spectral irradiance or spectral radiance. So what I told you is solid angle, radiance, irradiance, spectral radiance, spectral irradiance. If you want to find out total flux, simply integrate spectral irradiance, you will get a flux. If you want to get spectral irradiance, simply integrate spectral radiance, you will get flux. Spectral, irradiance. Next aspect is scattering cross section. Actually, I forgot to keep the figure forms. For example, you take Rayleigh scattering. Rayleigh scattering, how do you know how Rayleigh scattering occurs? Scattering occurs because just consider an atom. It takes place in molecules and atoms, correct? Because it takes place even bigger bodies at a higher wavelength. It is actually the ratio of wavelength into size of the particle. Let us consider molecules and solar radiation, this kind of radiation is falling on that. Atomic size is very small, less than of the order of angstroms. No, when your wavelength, your radiation falls on that, 532 nanometer, it's much bigger than the size of the particle, much bigger. That is molecule. What happens is, this as an electric vector and magnetic vector. It's as an electric and magnetic vector. If light is sent in this direction, electric vector can be in this direction, magnetic vector can, or it can, actually it has to be mutually perpendicular, that's all. Electric vector, magnetic vector will be mutually perpendicular, and will be perpendicular, both of them will be perpendicular to the direction of propagation. Correct. It's a simple thing. So, I assume that this is my electric vector, and it is going in this direction, it is linearly polarized. I just assume it is linearly polarized, simple. What does it mean? If I keep my point only at this location, the electromagnetic radiation is continuously passing. All what it means is, my electric vector is vibrating at the frequency of the light. That is frequency. So you observe only at one point. Don't look here and there. Only at one point. Just measure the electric vector length. And at one point it will be like this, another point will be like this, another point will be like this, then it will be going like this. Then come down, come down, come down, come down, and it will go reverse. Means the electric vector will be vibrating. What it will do to the atom? Electric vector is very big, its size is much bigger because the wavelength is much larger. And you have the atom. Atom is electrically neutral, or atom or molecule. Let it be, even molecules. What it will make is, it makes a small, if you apply an electric field into an atom, it will get polarized. Because nucleus and electrons will be slightly shifted. Not that all electrons will be put in the other direction and nucleus will come in the other. There will be small polarization developed, very little polarization. Means, if the electric vector is in this direction, electrons will be going in the other direction. So this will be vibrating like this, means there will be a polarization electric field that is generated in the atom. And then what happens? It is working in resonance with this, because this electric field changes, this also changes. What will happen is that atom start, electric vector of that atom, polarized, start vibrating. Same in phase with this, correct? Once you have an electric field that is vibrating like this, what it will do? It will emit the, it's like a dipole antenna, what you are getting. Your TV signal, what you are getting. Same thing. It will scatter in all, not scatter, radiate in all directions. Now you see, when I am viewing this atom and this was going in this direction, it was coming like this, I'll find that the electric vector is vibrating and I'm able to see the vector of the electric field. Correct? So it is as though I'll be able to see the electric field if I have an electric field detector. Now, a polarization electric field, it was vibrating like this, it reached here. I observed it like this. Now I'm observing like this. I will not see anything. You see, is there any displacement in electric vector in this direction? No. That's why the polarized light falls on an atom or a molecule. The scattering function will be just two circles joined together like this, double. And right at the place where the atom is there, it will be, I mean, what is it called, null point? It will be all joining together. You understood what I'm saying? This is a color value scattering. The scattering cross section, this line will look like this. What does it mean is, actually that line represents how much is the intensity of light that is going in each direction. Correct? In this direction, nothing is going. This direction, nothing is going. But then I told, if you are sending polarized light. Yeah. Now the polarized light can be in this direction or in this direction also. No, the electric vector can also be like this. Suppose I am still sitting here and the polarized electric field is coming like this and it is vibrating like this. Then looking from here, it will not vibrate like this, it will vibrate like this. Now I am able to see, but the fellow sitting there is not able to see. Okay. Now the light which you see in nature is unpolarized. There is nothing called unpolarized. All light are polarized. All electric will not go through random. It is systematic manner. But it is equal mix of part. For example, perpendicular polarization and parallel polarization are equally mixed. That is what is happening in sunlight. Then what happens? You will see both. But your scattering function will be then sum of two. One is if I am looking in this direction, a circle and a dumbbell. So effectively, it will not come a null point here, but rather like this. You understood or not? Maybe the picture is missing. You understood? Confusion? So if you don't understand, you please tell me. What I'm telling is this. I have an atom, and if polarize the light, electric polarization in this direction, like in this direction, and it is writing with this. This electric vector will vibrate like this. Clear? Then the intensity I am seeing from here, it will scatter. This radiation will be scattered in all directions. In all directions, intensity will be maximum in this direction, least in this direction, slightly less in this direction, still less in this direction, still less in like that. So effectively, it will be like this. At this point, it will down. This is a scattering function, which means I will not. This shows how much is the intensity of the radiation that this molecule has scattered is reaching. That line indicates that. Length of the vector indicates that simply. Otherwise, there is no meaning for this. And in this direction, nothing. Actually, it will be converted. I will not be able to see anything, provided electric vector is in this. Now, the electric vector is in this direction. Then I will see from here and here maximum. So, but then for viewing from the top, if the other thing is there. If I combine all these things in any direction, because now you have both this and this, and it is getting added to all these things, pictorially, it will be looking like. And so in Rayleigh scattering cross section, you will get this figure. Most of the textbooks will show this figure, not this figure. Okay. But in laser, for example, lidars, when you work, laser usually we opt for polarized lidars because it will be easy to handle in terms of inversion. If it is unpolarized or polarization impurity is there, it will be laser will be mostly polarized. But if polarization impurity is there, then it will be difficult to handle. So we say polarization impurity has to be say 99.99. That case we can ignore the other part. Then this becomes very important. Becomes very important in the inversions. If both components are there, your inversion becomes a little bit more involved. People may not realize that, but this is what is happening. Okay. So cross section means cross section means how much is the amount of scattered intensity going in that particular direction means per solid angle in r theta phi, r in theta phi in that particular direction by one molecule. By one molecule. So if I have 10 molecules, multiply by 10. So scattering cross section multiplied by the number will give you scattering coefficient. So usually what we 10 is not a number. Actually, then we will say that per meter cube. No? Per meter cube. So 10 molecules per meter cube. If I say that, then what I am going to do is cross section multiplied by number will give me coefficient. That's why the coefficient unit will be meter power minus 1. Because cross section unit is meter square, n is 1 by meter cube, coefficient will be meter power minus 1. This, you don't worry about it, I will come to that in no time. Okay. Just remember this, that cross section is by one molecule or one unit substance, whatever you consider, unit substance. If n number of substances are there, multiply by n, you will get coefficient. And if you integrate the coefficient, you get optical charge. Okay. So this is the way it is linked. I'll come back. I'm sure that you may have some confusion here. I will tell you what. This is scattering cross section. Cross section, what is the unit? Meter square. So there is no problem. Here, a single particle per meter, it looks as though how much is the area offered by that for this particular fellow to get resisted. That's all what it means. Now, I multiply by how many of those particles are there, I get total coefficient. Now, if I take the total coefficient is again for number of particles per unit mass flow. Now I am traveling from here to there. All what I have to know is how many of those units are there between you and me, that is the length. I multiply by the length, I get optical. I'll come to that. This is an important thing for you. So far, what I told you is only preliminary things which you already may be aware of. But what I am telling here, maybe somebody might have told you this, but it is important from a few other points as far as we are concerned. First thing is you have the fingers. You look at this I took from the textbook, this we measured and combined. This is spectral. This is something which I took from book. You see the top line. This is for a body at 5,900. That is the temperature. You can say that 6,000 Kelvin is the temperature. It may vary a little bit here and there. And in fact, if you are looking at the sun as a single point, then this is okay. But if you are looking at the solar surface, it varies from 4,000 to 10,000. It's a different thing. But we are not bothered about that because as far as we are concerned, 6,500 or 6,000 is fine. This is the black body curve for 5,900. Okay, this one. Now, what we measured at the top of atmosphere is, you see, there's a king sitting here. That way they give the light. But otherwise, it follows the black body curve, except for a few kings that comes one here and here also it can come. Extreme ultraviolet radiation also it will not follow the 6,500 black body curve. This is important for ionospheric films. For example, here the radiation will be looking like this, whereas black body curve. This is the way first time people inferred what is the structure of the sun inside. Because this particular fellow that is coming, if it whereas black body curve will go like this. Whereas you are getting significant amount of radiation. How it is possible? It's possible only if there is a body with a much higher temperature that is emitting. Then they inferred that solar surface contains much higher temperature at places, fraction of that. It is not a solar temperature is uniform. First thing is solar temperature is not uniform. The non-uniform thing comes mainly here that it contains much hotter surfaces. It can be chromosphere. It can be radiation that is coming from interior also, because solar interior is very hot. Only thing is, calculation says that the core temperature is about 1,000,000 degrees centigrade. But it takes almost a crore of years to come out, because sun is a perfect black body. So the photon that has come out from there will be absorbed by the next. There will be very, very trace number of photons that come out from there, but that is extremely rare. It takes long time because there is a large refractivity. It doesn't come like this. It goes multiple times, goes back and forth and escape. Very few number. Anyway, the 16,000, 1.6, the million temperature is not the one which passes. Million temperature would have been actually much higher. It would have cost much higher. But this is something like 10,000 Kelvin, 30,000 Kelvin. That's why atmospheric people are more bothered because this spectra, EUV, we say EUV, UV. First thing is ultraviolet radiation start from X-ray, gamma ray, EUV, UV, visible, infrared, near infrared, mid infrared, far infrared, and micro radio. This is the way it goes. So, in this domain, ionosphere will get at least radiation. This cannot cause any ionization because ionization potential of a species is there in a species. As an ionization potential, that means it requires minimum H nu to pull the electron out. This cannot do that. Only this part can. Anyway, I am not bothered about those things as far as we are concerned. The Planck's black body curve is more or less obeyed for most of our scale. Remember, the scale is, in logarithmic scale. Actually, it is log scale. Okay. That's why it goes like this. But what we reach at the surface, what we get at the surface is this. This is what you get. And it appears like a contour like this. And then suddenly it's here. And these places, nothing is coming from the sun. There are some wavelengths and nothing is coming from the sun. Nothing. You look at the sun, your eye is not anyway sensitive here. But suppose you have a detector which is sensitive to this wavelength, you can probably look at the sun is dark. This atmosphere absorbs completely. But not here. Here and all it will be very, very bright. Okay. So the question is, two questions. One, why you have this kind of much less radiation reaching the surface? It's obviously because of absorption. Absorption by certain species. It is already written here. Ozone, water vapor, ozone and water vapor together, water vapor absorption, water vapor band, here also water vapor. There are water vapor bands which will be absorbing. So, conventionally people will tell you that, atmosphere is transparent to solar radiation. It's not so. It's not transparent. Small fraction. That's why yesterday in our radiation budget calculation we said 23% is absorbed. Part of it comes. Okay. But notwithstanding that, you see this much difference is there between them at this level. And as you come down, that difference decreases. Why? Firstly, why this difference and this difference? Absorption, it is already taken care. Okay. Here there is no absorption. Even absorption is there, means it is very weak also. Photon is more or less. Why? Rayleigh scattering. Okay. Rayleigh scattering will scatter part of the radiation that is coming to the surface. It will be sent back. That's why people are, if you go to moon, you can see the Earth. Why? Because partly reflected, partly scattered. Correct? If no radiation was coming, you will not be able to see it. And you will see it, and you have maximum extension here. And then as you come down, this separation decreases. Why? That you must be knowing, because I already told the answer. Rayleigh scattering. How is the wavelength dependence? 1 by lambda power 4 means this wavelength will be maximum affected. As lambda power 4 increases, the effect decreases. That is why in the evening you see the sun has red, because blue has gone, yellow has gone, green has gone, red has gone. Because that is least affected. That's why railways have kept red as the signal. Because it will be traveling longer distance, it will be less attenuated, sensitive to the eye. Correct? So all these things come from, all these things are like this. So this is at the top of the atmosphere, this is reaching the surface. And at the surface itself, there are some places where this is if you want to calculate this, you have to know what is the amount of these substances. You have to know what is the cross section of those substances. Absorption cross section of those means how much is per molecule absorbed in that particular band. So it is not that I have say 400 molecules of water vapor. It will not help us. How one molecule will be absorbing at this wavelength and next wavelength. So you have to integrate it. Okay. So that's why that's actually about radiation control. So that you will exactly know. You can do the reverse way. You do this, you can estimate how much is the amount of water vapor absorbed present in that. But that may not be useful here, because here, whether it is 100 or whether it is 1000, both are zero. But here it will be useful, because it is never reaching zero. So if the water vapor amount is less, it would have stopped here. Very less, here. If it was not there, simply do that. So by taking the dip of this, you can do that. And taking the tip of this, you can do that. In fact, many of you have seen spectrophotometers. has a 930 nanometer wavelength band. Most of these are conventional support unless you are buying a most of it. One wavelength band. That is to detect how much is the amount of vibration. Because you make an observation here, one here, and you know that the difference should be coming linearly, but it will not come linearly. This much dip will be there. That dip has come because of what? Now you can estimate that what is the amount of water. So water vapor will decide how much is the radiation that is coming. But if you know how much is spectral radiance, you can estimate water vapor. Not only water vapor, you can estimate ozone. Actually, ozone meter will be taking some bands here, and of course, it will take in a. And this is what we observe. You know, we put a direct radiation. Direct means we look only at the sun. That is direct. Right directly from the sun, not from the environment. Means that is scattered. That's called diffuse radiation. So the amount of, even if I switch off all the lights, I'm not able to see the sun, still I get radiation. It's diffuse radiation. I will have no idea about the source. This room, I will get some intensity, but I will never know where is the sun if I am inside this room. Correct? Because diffuse radiation loses directionality. It can come from anywhere. But direct radiation will come directly unless you look at it. So you look at the sun, this is what you will get directly. I mean, it's a bigger one. This is the one which you will be getting directly. And this is the one which you will be getting from other directions. You take all other directions put together. This is the one. I told you, the unit is spectral irradiance, 1 meter square per nanometer. From nanometer per micrometer, then anything you can. And this, if I sum up, I get this. That is the total. So if you put a pyranometer, you will get this value, but you will not get this value. You will get integrated value out of it. Unless you put a spectrometer, you will not get this. This is spectrometer. The other one will be simply total amount of radiation that is some integrated value, but that's also important. So you have direct, diffuse, some of them is total, and spectral irradiance. So you will be getting these spikes. You can find there are a lot of applications for this, lot of applications, especially for aerosols and fuels, because diffuse radiation is a strong function of solar synthetic, and actually angle of incidence. So it matters. Direct radiation is something which is very So all what I told you here is only this much. Mainly, this is what is coming from the sun at the top of atmosphere, not at the solar surface. There is 1/4 r square change, where r is sun at distance. Okay. You know, in interviews, we used to ask a question. You can keep these things in mind. Any interview, you have to find the level of a candidate. Otherwise, the interview board is a failure. Means all candidates should be able to fail in some question. Don't fail them for failing sake, but fail them for gauging sake. Okay. And the fellow will have to fumble in some question. Otherwise, interview board is a failure. Because 10 people came, you have one vacancy. How do you take the fellow? 10 of them have That's why after coming out of the interview, everybody will say that I did not answer one question. All other questions. The difference is the interview board will be asking the toughest question. That one also did not answer. Even at the base level, if A cross B is not answered, then they will say, okay, go out and then get out. That will also did not answer the question. Where you did not answer the question. But here, if you ask them to draw a Planck's black body curve, most of them will draw a Gaussian curve. Some of them will draw. But if you ask them exact axis, most of them will not write exact unit. But they will say some energy, which is still acceptable. Then you ask them, what is the temperature? Then he will tell some temperature. You ask them to draw the same graph for other temperature. You can say this is 1000, you ask them to draw 3000, 300. They will shift to the wavelength and then 90% of the people process. One Planck's distribution curve is like this for 1000. For 300, the only thing which they think is wavelength will shift, peak wavelength will shift. So what do you do? But the fundamental principle is no two Planck's black body curves. See, those who study the basics will be able to answer. But question is not tough at all. It's a simple question. Left and right nucleus. Anyway, here what I am telling is this is the amount of radiation. As far as energy budget is concerned, how much radiation is this? This is the amount of radiation that we have reached at the surface. This much is lost to the space. And this is albedo. This is considered the albedo. And that is because of the molecular scattering, mainly Rayleigh scattering. But part of it can also come from aerosols. And part of it can come from clouds also. But bulk of it comes from Rayleigh scattering because aerosols are not there in high concentration at several places. And backscattering by aerosol is less. Not like Rayleigh scattering. Rayleigh scattering, it is equal in both forward and backward hemisphere. Aerosols, backward hemisphere is very less. Aerosol, somebody is speaking. Isoman. Now this graph is left part of this graph is the same. The right part is Planck's black body curve for multiple temperatures 300, 275, 250, 225, 200, 135. You see the verb length is changing. X-axis here is the verb number and this axis is the verb length. For example, you are something like 15 micrometer, 12 micrometer, you are 10 micrometer. This is verb length. And this 300 Kelvin will be peaking somewhere around here. Suppose my temperature is lower, it will be peaking here. Now, Earth's temperature is close to, suppose you say 288, 300 Kelvin, it will peak somewhere around. Okay. But you see, another thing is happening. Right here, this is actually what you see at space. This is actually by the satellite. This is not at the surface. This is by the satellite. Those holes are up. What it see is only this much is there. That it is this it is not. See, huge dip. Whereas surface has emitted this much, correct? Surface has emitted this much. It did not reach the satellite, means it did not reach back the top of atmosphere. It was wiped out. This bite out has come because of carbon dioxide absorption. And that is greenhouse. Because this much radiation is now trapped inside. The fellow is not able to see. I told you, satellite is seeing means it has to come from the surface to the top. So it is not coming, means this much is trapped here. That is because of carbon dioxide absorption, very broad band. And at 2, there is a problem. Not the problem, the advantage is it is almost at the peak. See, here something is there. If it was here, it will not cause much greenhouse effect. It is almost at the peak. Then you have the strongest absorption by carbon dioxide. That is why greenhouse effect is significant. Okay. So this is, just imagine if this was shifted this way or that way, your greenhouse effect would have been different. You can put the other way. Anyway, carbon dioxide absorption spectra you cannot change, but you are changing this. Surface temperature you are changing. So suppose temperature goes up, what is the kind of impact that it will have? That also is to be accounted for in climate change research. You have to take care of that. You may think that climate change research is simply about temperature. If you want to estimate this, you have to also find out 0.1 degree or 0.3 degree or 1 degree centigrade change, how much it will be shifting this graph, and how much it will be the absorption coefficient of carbon dioxide. Greenhouse effect. So this bite out is the greenhouse effect. This also is greenhouse effect. Okay. This is by ozone. This happens around 9 micrometer. Around 9 micrometer. Around 9 micrometer. So ozone can be measured from the satellite if you have observation beyond 9 micrometer. Those problem also there. And there are certain things here. This is by water vapor. This whole thing is by water vapor. You know, INSAT 3D and things like that. You know, satellites. I think it's nothing matter to. If you look the Earth in this, one thing which I forgot to tell you, this is called atmospheric window. Okay, 8 to around 14 is called atmospheric window because you see the radiation that is emitted is almost completely reaching there. Absorption is very less. That's why it is called atmospheric window. Window means what is emitted you are able to see. So it's a window. The other is a shutter. Okay, so this is called atmospheric window. That is why all the satellites for detection of clouds or surface and things like that will have one channel or even two channels. so that it can see the surface. Means it will see the surface emitted radiation, not surface reflected radiation. Remember, this is in IR. What we are talking is in IR. This is emitted radiation. Okay, so this is atmospheric emitter. Now, if I have two channels, one channel room here, there I am able to see, and inside 3D has another channel at around 6.7 micrometer. That is around here. There it completely deviates. You see, significant absorption by water. So you will never see the surface if you are using this wavelength band. That's why water vapor band or INSAT, you will never see the land morphology. Whereas surface, you observe in 10 micrometer, you will be able to see the boundaries because the land area will be having higher temperature in the daytime. So you'll be able to exactly control the land because it will have a brightness temperature higher than the ocean. Nighttime it will be reversing, that's all. But daytime will be clearly, very clearly demarcated. Whereas you will never see that kind of a feature. That's why people keep it. The advantage of that is it can detect even very small amount of water vapor. That's why it is called a water vapor window. I mean, sorry, water vapor band, not water vapor band. So upper tropospheric humidity can be detected. Not only that, you can detect thin cirrus cloud, even superficial cirrus clouds you can detect, which we have detected. We have a paper on how to detect the superficial cirrus by combining this in GR. Okay, so the graph will appear like this, but then your utilization depends on what you think. So this is a good base, but if you want to do any of those things, you have to have RT, radiation transfer. So that's why we are talking about radiation transfer. But radiation transfer itself is a full coursework, so we'll be only touching upon that. We'll not be going details. But this is what is essence of it. Actually, you can calculate how much is the surface temperature of any planet. Forget about any planet. It's a very simple thing. How much solar constant we told yesterday? 1368 watt per meter square. Watt per meter square. Earth is sphere, but if you put a ball against light that is falling on that, it will be making a circle. It will not make a sphere, make a circle. That means Earth's cross section intercepts this with radiation. How much? Pi r square. Pi r square, where r is the diameter of the radius of the Earth, for pi r square. No, not for pi r square. Pi r square. Pi r square is the cross sectional area into solar constant. That is what the amount of radiation that Earth is intercepting. But part of it is reflected. So 1 minus A. A is the albedo. That is the amount of radiation that the Earth atmosphere system is taking, not the surface. Earth atmosphere system is taking that is on the left side. Solar constant into pi r square into 1 minus A. This much is absorbed by the Earth atmosphere system. I repeat, Earth atmosphere system, not Earth, solid Earth. Now, temperature is remaining constant. So that means it has to re-emit. All that radiation is re-emitted. Re-emitted at a temperature sigma T power 4. So T is the temperature of Earth. This is called effective temperature of the Earth. Sigma T power 4 into, it is emitted through all directions. 4 pi r square. You may tell that no, there is a huge variation, polar radiation emits less, all those kind of things are okay. We are telling about Earth as a point, not Earth as latitude variation, longitude variation, time variation. As a point, or what should be the effective temperature of Earth? For example, today's global mean temperature, we may say, I think how much, 288.5 or something like that, 15 degree, 15.8, something like that, is the mean temperature. So, that is effective temperature of the Earth surface. Okay, so like that you are getting a temperature. You can derive this temperature for any planet. You don't have to go to the planet measure and all those things. That's the power of basic physics and remote sensing. A is already known. If you calculate, you will get T is equal to 255 Kelvin. Much less. Whereas you are actually 288. Yeah, 288 Kelvin is the mean temperature. That is, you want pen? 288 Kelvin is the global mean temperature. So there's a 33 degree centigrade difference Because in this equation, we just assumed that solar radiation came, it absorbed and it re-emitted. We did not account for, this is perfectly fine. This is perfectly fine, but we should know that this is effective temperature of the earth system. That remains constant. Whereas the surface will be warmer. So we have to, if you want to find out the surface temperature, you have to take out certain terms and put the greenhouse effect there. So greenhouse effect is effectively 33 Kelvin warmer. That makes 33 Kelvin warmer because of that whiteout that was taking place due to water vapor, due to carbon dioxide and all other species. See, a simple calculation will give you how much insight. And let me tell you one more thing. In future, when you say climate change is happening, what is happening is the altitude of this 255 Kelvin is the one which is changing. That's another way to look at it. Now you have a 255 Kelvin happening somewhere, maybe at maybe around 7 kilometers, somewhere around there. If later on, climate is changing, it will be still 255, but that 255 will take place at another altitude. So effective radiative altitude of the atmosphere goes up. This is another way of looking at it. Okay. Anyway, they are all only your thinking, and then this thinking has another dimension. Okay. In climate change research, this what I told us huge implication, but we are not discussing those kind of things. Somebody else may talk. So this is important for you to know radiation transfer heat. How much is the amount of greenhouse effect and this way. And I already told you about this satellite measurement over Sahara, how much it was doing, and how much is the work, whiteout by carbon dioxide, and which wavelength band. So remember this wavelength window region is around 8 to 12 micrometer. Okay, you can say even 14 micrometers. 8 to 14 micrometer, where atmospheric window. See, it has come here. This is atmospheric window, means most of the radiation that is coming is like that. Of course, there is some small amount of substance will take place. This is completely vital. That is greenhouse effect of carbon dioxide. But not just limited here. We still on either side there will be some amount. And you see here, this is ozone. LA graph was in frequency, this is in wavelength. That's why it is looking ultra. Okay. So this around 9 micrometer you have. And still further you have significant change in temperature. Why I am telling significant change? My reference is this one. See, here is what it means. So this is what the body has emitted. What the fellow received is this much difference. And here, this much difference. So this is the kind of absorption that they use. Not you compare with this graph. No, you compare with this graph because this is the one which is understood. This we already explained. Part of the radiation that is going, emitting is going and then coming back. That is what is called carbon dioxide. Greenhouse effect. And greenhouse species is carbon dioxide, water vapor, ozone, and there are several other fluorocarbons, methane. Methane is very important. Methane is very important. This is an important. Now we are actually entering into a little bit on the radiation transfer. While doing this, so far it was storied. Actually, the top graph shows the absorption spectrum. Absorption spectrum means now this is wavelength starting from 1 micrometer to 30 micrometer. And at each wavelength band, this fine light you have to consider when you are doing radiation transfer. You cannot just average out all these things. It's very, very fine lines you have to consider. There are two options. Option number one, instead of taking very fine things, you take some small bands. And you average, which is okay, primitive. That's called a band radiation transfer. But if you really want to do, you have to go for line radiation transfer. That means ultra fine lines you have to take and then do the radiation transfer for individual lines. It's called line radiation transfer. That is much more complex. No, effectively what I am telling is how much is the transmitter to the atmosphere is what is shown here. You see, some domains absorption is very weak. You see, absorption is very weak here. Very weak here. Because the y-axis absorption. Top reaching means 100% means fully absorbed. So radiation at this band is fully absorbed. Earlier we have seen 1.6, 2.1. I told you, solar radiation never reaches the surface. It is fully absorbed by blue. Blue is water vapor, and this is carbon dioxide. Where is pink? It is a mixture of both. Blue is water. This is carbon dioxide. When blue and these are mixed, you get emission. You have to know this. This is mainly from water. There is a small thing which comes from carbon dioxide. And here again there is full. Here again there is some finite amount, and then you have carbon dioxide. This whole domain is absorbed by water. Nothing is allowed. Ozone absorption band, I think, yeah, it is not marked. 9 micrometer. Actually, this 9.5 should come here. Partly this should have been contributed also by ozone. Actually, ozone is not standing alone. There is a small absorption by carbon dioxide. It is overlapping. That's why they put only carbon dioxide and water vapor as far as this is concerned. At most of the other places, it combined. It is mix of both water vapor and carbon dioxide absorbs. Okay. That's why, but mainly carbon dioxide is absorbed. And some amount by water vapor. The radiation transfer for the whole domain, if you are taking line by line, it takes a huge amount of time. And for each angle, for each pixel, for each time, it's a lot of things, and effectively you will not be able to do. It's like something like huge computation time and huge data. You see, line by line, satellite has to transfer the data. That's why most of the observations people take band. For example, thermal infrared band 10.5 to 11.5, 11.5 to 12.5. It will be still small only. See, 10.5 to 11.5 will be nothing. And 11.5 to 12.5. That's all. Not that they will average the whole thing. This shows the actual value of absorption coefficient. This is transmittance, that is absorption or transmittance. Inverse is transmittance. Inverse means different, one minus. And this what it means is how much is the absolute value of scattering coefficient at each wavelength time. For 0.8, this is 10 micrometer, this is 100 micrometer. So you will get by liquid water, water vapor, or ice form. This is not for atmospheric species. This is for clouds. Cloud in liquid form, cloud in vapor. I mean, water in liquid form, water in vapor form, water in ice form. How is the reflectance? Look at this. Vapor has, that is omnipresent. Water vapor is omnipresent, but its absorption process will be smaller most of the time, and it is going as undulating as light because it is still behaving like a molecule. Molecules will have this. Whereas these things are much higher, okay, in magnitude. So, for example, if you want to discern clouds from water vapor, dust is around this time. The absorption, absorption cross section is very high here. By water vapor is much smaller. So correction required here becomes very small. That's why the brightness temperature which you are observing can be converted to cloud top temperature. But if this was not the case, you will not be able to convert it directly into cloud top temperature. Because you want to know what altitude is the cloud. So only information that you have is the brightness temperature that you are observing from the black body. So how much is the temperature? You can convert with an assumption. Still there will be error by maybe around 5 Kelvin. So that is okay. But here and all you cannot do that because water vapor has an equal contribution as the clouds. So if you observe it in this man, it will be very difficult to find. Okay. So in your radiation transfer, you have to account for all these individual lines if you really want to estimate any of those kind of fields, whether it is cloud, ice, or cloud water, or water vapor. And all of them are present together. So this I am repeating. Around 10 micrometer, where you have the thermal infrared channel for satellites in satellite, or any global geostationary satellite will have a channel here, mainly to detect clouds, because the amount of water will change influence of water. Okay. I'm only giving a gist of the thing. I'm not going into the details because that much time we don't have. If we have time, we will talk about this graph itself for hours.
So for the thermal infrared band, you consider like one wavelength or
actually it's a band. No, it's a band. There's a filter that is put in front of it. Like for example, now my eyes are able to detect the colors. That's why I'm able to differentiate. Detector is not able to. Detector cannot have color differentiation. Any detector cannot have color differentiation unless there are multiple detectors kept. For example, if I have 3 detectors, red, green, blue, I can disseminate any color. I can find out what is the color because red, green, blue concentration will be different. Alright, means I have to have 3 detectors if I want to detect color. A single detector will not detect whether it is red, green, blue. It will detect whatever it is. So, double infrared, 10.5 to 11.5 is the band. Whatever radiation it is coming in that, it doesn't matter whether it is 10, whether it is 11, whether it is 12. It will be taken as one band. If you are using a spectrometer, then it can differentiate between 10, 10.1, 10.2, 10.3 like that. These are all images. Insert 3D insert image. There's no spectrometer. So it cannot do. But you asked a very relevant question. Let me tell you that. I have one at 10.5 to 11.5. We also keep 11.5 to 12.5, one more detector. Why unnecessarily we are keeping two? Because both are almost the same. You see here. It doesn't matter whether it is 10.5 or 11.5. 10.5 to 11.5, 11.5 to 12.5. It doesn't matter much. But most of these INSAT or GOES or FI2 or all these are geostationary satellites. Or Himawari or Meteosat, all of them are these. No way. You said, can you differentiate in spectrum? You cannot. But I have now 2 bands. Here you see this light is fixed. If I take this much, here the red portion is not. I have 2 bands, one band here, another band here. Here, this is missing. This is what? Carbon dioxide and water vapor together. Here only water vapor is in this band. Means if I make these 2 observations together, first thing I assume that the temperature of the body remain the same, that brightness temperature remain the same, which is correct. Then what is happening? My radiation is absorbed by water vapor above the cloud. Little bit. Here it is purely water vapor. I can have an estimate of how much is the water vapor if I have these 2 bands. It's called a split window technique. In radiation in remote sensing, there is something called a split window technique. That's why these 2 wavelengths are put together. That's 10.5 to 11.5, 11.5 to 12.5. You take the differential, you will be able to find out how much is the water vapor. But still, there will be small inaccuracies. Here we assume that they are of equal concentration. Some inaccuracy, but that's okay. Then, if you know how much is the water vapor above the cloud, you can correct it for the temperature. So you can actually derive the cloud top actual temperature, provided you know the emissivity of the cloud. Emissivity of the cloud can be modeled if you know the cloud phase. Obviously, ice cloud. The phase will be in ice form. You know how much is the emissivity. You can correct for the actual temperature. That will be still in error, maybe by 1 Kelvin or 2 Kelvin, but you are in business. Most of the people don't do that. Satellite, what you are getting is a brightness temperature, and we all play with that. But if somebody is really interested, you can go for this split window and then do this. Actually, we did. One of my students was there that time. That time we, if you, what you do is you just take 10 micro, 10.5, 11.5 and 11.5, 12.5. You just play with the images. Both of them will exactly show the same image. You just take a difference, entirely different image. Because absolute value is the same for both. No, minuscule difference is the one which you are getting. So you'll get for heap clouds, you will get a complete reverse pattern in one channel compared to the other channel. Because that fellow was able to detect water vapor above that. The other is not affected. So, but a detector cannot differentiate this unless the amount of radiation that is falling on the detector is filtered to that level. Detector may be the same, even for 10.5 and 11.5, detector will be the same. But the amount of radiation that is falling, there will be front-end filter that is kept on that. So the filter will not allow. I put an yellow glass. No other radiation will come. But my eye is able to detect yellow everything. Only thing is that still I am not going into the details, but there's a quantum efficiency and things like that for that detector which you have to correct. Anyway, that is experimentation. That we will not deal with, otherwise you will not be able to complete any of these. So this is what the absorption spectra looks, and this has to be now converted for optical depth, radiation transfer calculations, heating rates, and all of this. This you should know. I put mathematics minimum in my presentations, but this you must know. It is the simplest equation I have ever seen. How much is the optical? What is optical? Because most of the people again fumble at these kind of places. They say optical depth, what is the dimension? Depth means distance. Now it's a problem. So they'll say meter and all those things, but it's a dimensionless quantity. Okay. So, Bowyer-Lambert, people will be writing Beer law or Bowyer-Lambert law. In physics, most of the time what happens is multiple groups have worked on the same problem. So somebody else will combine them and then make a Beer, Bowyer-Lambert law. Not that they worked together. Beer law was different, Bowyer-Lambert was different, but then they have the same form. So I am telling you now, I have a medium. Now that is your eye and my eye. That is the medium, or your face and my eye, and the detector. You are the emitter or reflector. Some radiation reflects. I am not seeing actually the amount of radiation that you have reflected. It is attenuated between us by Rayleigh scattering, by molecules, by water vapor, by carbon dioxide, all those kinds of species. If I want to find out how much is the effect of attenuated radiation, I have to calculate how much is the extinction of radiation that takes place. Extinction means gone. How extinction will take place? By either scattering or absorption. It can be scattered out. The photon was coming, it got scattered out in the other direction. So that is lost. Remaining photon only come. Correct. Extinction means that photon was absorbed, remaining photon only come. So I have to know correct for how much is the absorption that is taking place between us. So what you do? What you do is you find out how much is the absorption that is taking place in a small length. Integration, what we do? We cut it into small pieces. DL, DS. So I have a line from here to here is traveling. I will take out a small portions of dx, dx, dx. And I will find out how much is the extinction coefficient at each point. But it is very difficult for me. Between us, how much is the extinction? So what I will do, I will assume that this atmosphere has certain properties and integrated property only I will take. That integrated extinction. So integrated extinction coefficient from here to here, alpha is put. Multiply by the intensity is the one which per unit distance if I travel that much radiation will be lost. Multiply by dx is the radiation that is lost in a small. So how much is the radiation that is lost when a beam of light is coming to you? Is how much distance it has traveled and how much is the radiation attenuated within dx, and there the extinction coefficient is alpha. So extinction coefficient becomes very important. Okay. And if I know this equation can be simply converted to this. Okay, because this is Pi. Now I have to integrate how much is the total radiation that is lost between us. Because this is only for this one, B is only for dx distance. So how much is the total distance that is? So you have to integrate from 0 to L. This equation. You get this. Integrate 0 to L. Because all other things remain the same. Alpha dx is now means integral of the extinction coefficient is optical. This has a lot of physical meaning. Extinction coefficient unit is meter power minus 1. Multiply by meter, it becomes integrate optical depth is what is optical depth and extinction? Extinction is the one which will be extincting your radiation. It is nothing but similar to optical depth. But what is the difference then? Extinction coefficient is per unit length. How much is the radiation extinct per unit length? That is meter power minus 1. In 1 meter, how much is the extinction? If I integrate from the source to the receiver, is optical. For example, sun is there. I know how much is the amount of solar radiation coming from the sun. We know, we have seen already. Okay. I know how much is the amount that is getting here. You have photometers, you just look at you will be measuring how much is the radiation. Coming here. It's very easy for me. I is equal to I0 e power minus tau. All what I have to find out is tau. So I'll find out how much is the tau. Because I measure. I0 I know. That is the it doesn't vary much. Okay, it varies little bit, not much. That you have to correct for. That little bit variation is solar electricity and the what is that called? Inclination is there, na? Season. That you have to correct. That is easily correctable mathematically. So, I can factor down the atmosphere is sitting here. I don't have to travel anywhere in the atmosphere. But then, by doing that, I don't know whether that absorption took place at the upper troposphere, stratosphere, mesosphere, thermosphere, or at the ground. It has taken place somewhere. Integrate. It may vary also. So this tau I will be able to do. But actually, tau is constituted by molecules, water vapor, molecules, trace gases, clouds, aerosols, all these things. So this tau is actually total, that is equal to molecular, aerosol, cloud. And molecular include two functions. One is Rayleigh, second is absorption by species, depending on what wavelength band you have. Because this is a wavelength band function. 9 lambda. Okay. You understood or not? Is there any problem here? It's a very simple thing. This is called Bowyer-Lambert law. Bowyer-Lambert law, all what it says is the amount of radiation that is extinct will be proportional to the amount of radiation that is falling multiplied by the extinction coefficient and integrated over X. You will get the optical line. And I is equal to I0 equivalent. In an interview board, if you write this equation or this equation, it is okay. Bowyer-Lambert law finally gives you this. But basically, this integral form, because BI, I comes in the denominator, it becomes logarithmic, that's why you understand? So this is optical thickness, and remember this is dimensionless. So optical depth is 0.3. 0.3 what? 0.3 chakka, manga, nothing. 0.3 is 0.3. So this is the integrated extinction coefficient is optical thickness. And the optical depth which you are measuring by this equation is actually the sum of the optical depth. Now you have to subtract how much is the molecular depth. So you know Rayleigh scattering. So you can subtract. You know how much is the absorption that is taking place by whatever. If you know. So what you do is you don't observe in absorption bands. You observe in outside absorption bands. Otherwise you have to correct for that. It's very difficult because that's really you have to already know. And aerosol you can finally get. So that's why your sun photometer will give you AODs this. Because what that fellow does is only it measures this. It knows this, it will find out this, and it will subtract this term, and cloud should not be there. So this term is not there. This is band radiation transfer. This is not line radiation transfer because you will be making measurement at say 530 nanometer, 600 nanometer, 700 nanometer, like that. At a band, maybe bandwidth maybe 10 nanometer. Okay. You will not make it line. This is a most primitive form of Bowyer-Lambert. The next is emission functions. I did not put it here because that is a little bit more involved, and that is not required.
Optical tells you about how much radiation is scattered and absorbed.
Absorbed both. But you don't know. Very good question. Actually, you don't know whether it is because of absorption or scattering. The third term comes now. Single scattering albedo. Now, aerosol is the one which is giving you the optical thickness. So optical thickness is say 0.5. Out of that, how much is absorbed, how much is scattered? No idea. What you got is 0.5. That's all. But if you want to know that, you have to measure how much is a single scattering albedo with another technique, like nephelometer or something like that. Okay, or you have to model it. You can model it also. For example, if you are measuring black carbon, you can model it. Most of the absorption comes from black carbon. Little bit from the other species, but you can model it. Dust also absorbs in some wavelengths. Okay. So typical value of say I say that single scattering albedo is 0.9. It means 90% is scattered, 10% is absorbed. Single scattering albedo 0.9 means 90% is scattered, 10% is absorbed. But single scattering albedo of black carbon may be 0.2, means 80% is absorbed, that's why it is black, and 20% only scattered. But typical value of single scattering albedo for our ambience can be, it will vary. It can vary from 0.6 or 0.7 to maybe 0.95 kind of. Pure non-absorbing thing will be 1, but it is very rare. Typical value can be of the order of 0.9, 0.85, 0.9. Here, in this condition, it may be 0.9. Typical value. I'm not telling that is the value. If this part is clear. Actually, I did not put this here. So this is called the generation gap. You people can put things very fast, graphics. I cannot. It's an old machine. Okay. So I take time to put the proper graph. I did not get. Well, there are plenty of graphs which are available in my computer itself, but I could not locate it. But instead, I will tell you because I know what it is. I told you Rayleigh scattering will be symmetric, both forward, backward, and right at the center, nothing. But if you have unpolarized light, a dumbbell. So this is fine. This is the way it is comes. And this is the way it looks. The figure is not exact, but it is symmetric. This way you take, or this way you, this hemisphere and this hemisphere, both are equal. So if I take something in this direction, which is fine. So you take the scattering angle, this radiation has come in this direction. So scattering angle, this is 180 degree, this scattering angle is 0 degree. Because it just went forward. If a radiation has come back, it means it is back scattering. So scattering angle is the direction and then coming back. 180 degree. We put the phase function for this. Phase function means normalized value which is getting scattered. And this angle is 0, 180. Here is 90. It will look like this. Maximum at 0, minimum at 90. This is Rayleigh scattering phase function. Means at each angle, how much is the relative intensity change that is taken? This is a normalized value. Normalized. If you want to get the actual value, you have to integrate it and multiply by the scattering cross section. That's why you are doing. Now for aerosol, this is not the way. For aerosol, this will look like this. If I have a bigger size particle and whirling this, very little will come in this direction. And most of the radiation will be going in the forward direction. Okay. So you remember, this is actually more or less smooth it is going. Whereas here you have multiple humps which are coming in the backward. This is one characteristic. Second characteristic is this is completely unsymmetric. So as the particle size becomes smaller, if the particle is becoming very small, then but if the particle is becoming larger, this pillow will be further narrowing and then going. And this factor becomes smaller. Okay, still smaller. Bigger the particle, smaller. Smaller the particle. But bigger or smaller the particle is only a relative term. Relative to what? The wavelength that it is. So always take a parameter called 2 pi r by r is the size of the particle, lambda is the wavelength. So otherwise this size, high, low and all those things have no meaning. Correct? Meaning comes from size parameter. This comes size parameter. Okay. So if the size is still bigger, then most of the radiation will be going in this and very little in the backward. So this is called the mean scattering. There's a method to derive all these things. There's a book called Van de Hurst. If you read that, you will know how to do mean code, how to develop mean. The first term of mean code is Rayleigh scattering. Okay. Subsequent terms of mean code contains multiple things. Very first one, Rayleigh. That is first smallest. Then multiple things are getting added. Why this is happening is because when a wavelength and this body is comparable, it no more sees it as a dipole. Earlier I told you the wavelength is very big. So the particle electric field, a pure electric field will be vibrating like this as a single body. Whereas the particle size becomes comparable to the molecule. The wavelength. Then it sees not as a single pole, it sees multipoles. So composite of the multipole is what you are getting. That's right. Here the phase function will look like this. Not be 0. Phase function will be actually not even like this. and there will be a small hump. This minimum here and a small hump. Okay. So this is the way. Like actually, it can be, it may not be even like this. Okay. So people do a first approximation for these kind of mathematical functions. It's very difficult to put it in mathematical form because each of these values you have to feed. Is very difficult. So what people do is they put approximations. One approximation is called the Greenstein function, where we simply putting it as a fitting like this. Single term Greenstein function will look like this. Double term Greenstein function will, but the actual value will never be output. It will be fitting. So that radiation transfer becomes very easy to do. The parameter called asymmetry parameter. This asymmetry parameter, just to define asymmetry parameter, the whole function will be defined by any function. By just giving one value, 0.7 to give, the phase function will be more or less reproduced. So that is what is approximation. But actually you have to derive it. And nobody has observed this phase function. Nobody has observed. All what they do is, for example, Neplometer, what they do, or any other people, they will make observations at multiple angles. They never see all 360 angles. But again, you see one here, another here, another here. So this kind of small humps you see, it is real, but you will not be able to see in the real phase function calculation because that much, I mean, observations are not there. It is not even possible to make because this is backscatter angle, no? The light is falling on that. Light is falling on that. Light is has to be taken back in that direction. How do you observe it? You cannot observe it because light is going in that direction. Light is coming back in the same direction. How do you observe it? So virtually, there is no observations made in this direction. Very similar is the case here also. There is no observation because detector has to be kept right here. Light is also falling on that. That's why Neplometer has an angle over which it makes we make it here. Not see the full. Like I cannot look at the sun. Okay. Sun directly means it will be a huge problem. A huge problem means I will not be getting, you will get. What I am saying is you will not get whether it has come from the sun or it has come from the scattered radiation. That's all. Because scattered, the direct evidence will be very high compared to scattered. So there are some limitations to this, but then this works in first order. If you do with the radiation transfer calculation, how much is the flux that you are getting, you will be able to reproduce it within 1 or 2 hours. That's called a scattering phase function.
I will consider our particle size to be less than 0 micro.
You will get an effective value. You get an effective value, and the effective value will be
Can be into another smaller particle.
No, actually it will not be like that, but it will be superposing. For example, you have between us itself, there are so many particles. One may be 1 nanometer, other may be 100 nanometer. All these particles scatter. But what you are getting is a single value of radiance that you are getting. So it is effective scattered intensity what you are getting. So what you will also get is the effective size of the particle. You will not get the actual size of the particle. And remember this question has another meaning. The light that we see is intensity. It's a scalar quantity. You are not getting phase of that radiation, are you? Light is, electromagnetic radiation, it is oscillating like this. You are not detecting it. You are detecting intensity. Intensities are simply getting added vectorially. Not vectorially, scalar. 10 photons, 20 photons. That's all what you see. There's a place where phase is detected. That is in radar. In radar, they detect phase. That's how they are able to measure Doppler. Anyway, as far as this scattering is concerned, this is simply intensity. Intensity from small, intensity from big. So you are not able to discriminate between whether it is big or small. So what you will get is the effective. But now I want to know the size because I have to know the size. This is a method. The method is you have I told you that the scattering function will depend on the size of the particle. So lambda of r. So I have a mixture of r. Okay. For different lambdas, it will behave differently. So I measure spectral optical length. This axis is tau. Sorry, this axis is lambda. This axis is tau. tau at lambda. I get on this particular wavelength, I get value here. This particular wavelength, I get value. Correct? If I get multiple wavelengths, now the wavelength dependence has come from being what? Size of the particles. Because size parameter has come. This I can invert back. This inversion is called the King's inversion. Okay. If you get around 10 basically, you'll be able to get a shape constrained free, and I mean, you don't get complicated by this word. Means that fellow will not assume any shape. You will get any shape. Like for example, I will be able to get size distribution. Size distribution is what? dn by dr versus half. Like differential number in each size range versus size of the particle. This is what size distribution is. I'll be able to get like this, or if the function is like this, that also I'll be able to get. If I have not 4, I have 10 or 27. That is what is. So with a sun photometer, you cannot derive this. With a radiometer, which SPL has one radiometer, 10 wavelength bands. Size distribution of the particle you will get. But that is not obtained from individual optical bands, but from spectral variation of optical bands. Because the particle cluster of particles will behave differently at different wavelengths because of this. You can invert it. But then with the 4 wavelengths also I want. So what I will do is, there are approximations. You know, most of the time in nature, size of the number of smaller particles is much bigger than number of bigger particles. So I assume that this is size of the particle. This is dn by dr. That is number of particles in that. Usually it follows like this. Means number of particles in small sizes is much larger than the other. So this is, I already put a power law. This is called power law distribution. Okay. I already put a power law. But then what I'm trying to do? What I'm trying to do is, you can find out whether it is like this or whether it is like this. If I have 3 wavelengths, I can do this. That's called Angstrom parameter. Or what I derive is the slope of this. The slope of this is called the Angstrom parameter. Okay. So you will be able to derive size parameter from that. An index about the size distribution. If you have only 2 or 3 wavelengths. With 2 wavelengths is sufficient, but I put 3 wavelengths because 2 observations are not sufficient for fitting in proper. Then a small error comes, this will lead to larger error. Put 3 wavelengths, you will get correct. And most of the research which you see in aerosol, they will be reporting this value. Angstrom parameter. There they assume size distribution is power law. Power law means the power R. R to the power nu, R to the power nu. Size will be decreasing like this. So you can still get the number of particles with each size. It will not be exact. It's an approximation. If you want to get more exact, put 10 wavelengths, do King's inversion, you will be able to do it. But that also is not absolute, but you will get better idea. For example, a second spike is coming. You know, most of the time, aerosols here will be, small particles will be there and there will be a second hump. For example, sea salt aerosol. Wind, with the wind, you know, there will be a second wood that will come out. Because sea will be agitating and then sea salt will be moved and bigger particles. Such things you cannot detect with this. So, yeah, good. Now comes, yeah, sure, you ask her.
So I don't know. So radiation is coming from the sun and up to Earth, they are measuring the altitude. So how the optical waves will be related to the wavelength? All type of
Optical depth, as far as sun is concerned, and if only atmosphere is there, optical depth is value optical depth. It will vary as 1 by lambda power 4. Good question. 1 by lambda power 4 means wavelength versus optical depth. It will be varying drastically as lambda to the power -4 because Rayleigh, that is a Rayleigh scattering cross section. Wavelength difference. But if it is for aerosol, it can vary depending on the size of the particle. A thumb rule is, but that's a thumb rule, is lambda to the power -1. Lambda to the power -1. for aerosol. But that is not fixed. It can be lambda to the power 0. It can be lambda to the power -2. Possible. But the thumb rule is if somebody is asking you an order of magnitude, I want to do a quick calculation. Lambda to the power -1 will be more or less most of these kind of aerosols which we see. But it can be lambda to the power 0, means it will be flat if the particle size is very big. For example, dust. Dust is very big, it will not have any wavelength dependence. Okay. Cloud size is still bigger. Why cloud is white? Why cloud is white? Cloud is white only in the wavelength band that you see visible. You are only able to see a short wavelength band, that all the radiation transfer which we do, our eye is not able to see. In that wavelength band, cloud is white. Why? Because it scatters equally in all wavelengths. It is not coming to this domain, it comes in geometric optics because particle size is bigger. It cannot resolve 0.4 wavelength, 0.5 wavelength, 0.6 wavelength because particle size is big for clouds. So it will reflect equally in all wavelengths. Equally means not exactly equal, but more or less equal. So you will not be able to differentiate. So it becomes white. All wavelengths put together in equal intensity is white. Whereas, this is a good question. It has another meaning. Whereas if I observe purely sea salt, it will have a hue because it scatters more in the smaller wavelength, less in this higher wavelength. It will be all the more the case when you have very small particles. Sea salt is slightly big. It is all the more when, for example, it can vary as drastically, maybe even lambda or -3 it can vary. Means it will be scattering more in the shorter wavelength, less in the smaller wavelength. All what you see is a color, correct? The composite color. So it will have a hue. It will not be white in color. It will be having more preference for the lower wavelengths and less preference for the higher wavelength. Correct. Now I add little bit absorption to it. That is single scattering albedo. Part of the radiation is absorbed by black carbon. It is a mixture. I get a brownish shade, brownish color. Because it has a wavelength dependence, so it is not white. White will not have any wavelength dependence. All wavelengths will be coming equal. Solar radiation is there. Solar radiation contains, we are talking about only 0.4 to 0.7. We are not talking about the whole spectrum. That place most of the wavelengths are comparable. I am not saying exactly same, comparable. These are all only order of magnitude. Even white is only a feeling. It is not purely white. So now I am putting a lot of aerosol. What will happen is I will get a hue. Hue means a wavelength dependence of the color. And when you composite, it will not be white. It will be having slight color difference. If I add little bit more absorption, that is wavelength dependent, it becomes gray. Gray or brown. That is why this aerosol over the Indian region during winter time, it is called a brown cloud. And that led to a political problem. Because Indians are brown color. They said it is a racial discrimination which you are doing. Because you are calling it as brown cloud. But actually, when you see, yesterday my last talk, last slide was a brown cloud. Actually, there is a cloud immersed in aerosol system. Cloud is white. Brown is the aerosol size, and the aerosols, cloud immersed in an aerosol system also appear as brown cloud. But actually, brown cloud, what does it mean is it is not referring to cloud. It is referring to a cloudy, hazy, cloudy brown shape, a burned curry. Okay, that's why it is called a brown cloud. Cloud is never brown. Cloud is always white. Cloud cannot be brown. But when it is immersed in that kind of a system, you get this kind of thing. Do you see the question dimensions now we are talking, wavelength dependence? All these things come from radiation transfer. Because radiation transfer only will tell you, and this wavelength this has come. So far what we are talking is English. And English will not do for science. You require calculations, exact number. Okay. So now we will move on to the radiative heating rate. It can be for cloud, it can be for any other species. How do I estimate how? Now I am telling aerosols are there in the atmosphere, correct? Some place aerosol may be higher, some place aerosol may be lower. Some place cloud may exist, cloud may not exist. There's absolutely no point in taking total optical depth because total optical depth will give you an integrated picture. I want to know at which place of the atmosphere what will happen. Which place of the atmosphere will be heating, which place of the atmosphere will be cooled. I want to know. That means I have to know what is the altitude variation of the heating function. This is most fundamental if you want to do, the next level of aerosol or cloud studies, other than simply reporting AOD or cloud optical depth or cloud. Yeah.
So I am not. When we are calculating the optical wave, we taken a small
Wavelength. Small wavelength.
band dx.
Not dx. Dx is infinite because optical depth is from sun to here.
Yes.
Dx is very high.
It is our Earth atmosphere.
Huh.
So near to the Earth, the number of particles
Will be higher.
higher. How will it?
But you will not know. Optical depth will not tell you that I have more number of particles below and less number of particles above. All what it gets is, this is a column abundance of the particle. It is the column value. Optical depth is column value. Now if you want to, yeah, your question is correct. I want to estimate how much is the value at the base and the top, because that is more important. You require a LiDAR. You take a LiDAR, send the light up, pulse the light. It will be scattered back from different layers. You send a pulse and take a time series of the backscattered intensity. The first thing has come from the near area. Farthest point will come from the last point. So you will get an extinction, you will get a backscattered intensity variation, which you can invert back and find out how much is the altitude profile of aerosols. Same is the case with the altitude profile of clouds also. Only thing is clouds, you cannot profile with a LiDAR because cloud optical thickness is very high. You will not, for example, when a cloud is there, are you able to see the sun? No. So not even sun is seen. And forget about laser. So there you require radar. But thin clouds you will get. Thick clouds you will not get. Thin clouds you will get. Okay. So that is important. And that comes here. If I want to get the altitude profile of the heating rate, because where cloud is there only absorption will take place. And that too, it will not be uniform. It will be varying depending on the, I think 12:30. Up to what is your, what time is your office? No. I think there is, every holiday at the afternoon. City is blocked after 2. I see. But BSSC used to send the vehicles back by after lunch. Anyway, up to what time we can go? Now, I am getting the altitude profile of clouds or aerosols, whatever the thing is. I have let me tell you, this is the extinction coefficient. Extinction coefficient is alpha, and this is the altitude. This is I'll get like this. So you have much higher values at the surface, and you have an elevated layer also. This is for aerosols. This will cause a heating more here, less here, and more here. Correct? Means the heating will be, because you have more abundance here. Here you have more abundance. In between less. And that means the atmosphere column in this place will be more heated, this place less heated, this place more heated. That heating will drive the pressure gradient. That will drive again the circulation. It will have a lot of other impacts. So I have to get the heating rate. So how do I get the heating rate profile? What I do is I find out what is the alpha. Then I slab it like this. I make it into thin slabs. Okay. And I take one slab from here. The slabs is what I have drawn. Now I have put only 3 slabs. And there are infinite slabs. So I can do it for any slab. So I take only 3 slabs. Of course, other slabs you can do. This is a repetition. For I is equal to 1 to 100, you can do. How much is the amount of downwelling flux that can be short wave or long wave? Because solar radiation comes and longer radiation also comes. Okay. How much is the downwelling at the I+1 layer? That means my layer and above the layer. Above that layer, how much is the thing coming? And below that, how much is the thing coming? So how much is entering? How much is exiting? The difference between them will tell me how much is accumulated there as far as downwelling short wave flux is concerned. Same thing, downwelling long wave flux is concerned. So I have 2 terms already coming. Now, from the surface, it will go back. Okay. How much is the upwelling flux entering the slab base and leaving the slab top? Find the difference between them, I will get an accumulated value. This accumulated value plus this accumulated value is the total amount of accumulation of radiation that is taking place there. So this much accumulation of radiation has taken place in watt per meter square over DC. Rho F by rho C. This will be directly giving me the heating rate. If I know rho F by rho C, this is the heating rate that it will produce. And all what I know is Cp I know, rho that's I already know. So I get the heating rate by that species if I know how much is the rho F by rho C. Now I'll tell you a practical problem. All these things take place in an ambient atmosphere, whether aerosol or there or not, still you have downwelling flux, still you have absorption taking place here. All those things are still taking place. So I have to find out, say, cloud radiative forcing or aerosol radiative forcing. What I have to do is, I have to remove the effect of atmosphere. So I do a calculation first for clean atmosphere. Only atmosphere is there. Okay, no aerosol, no cloud. Now I do for an atmosphere with the cloud by putting this profile. Because in the beginning there is no profile, there is only zero. Now I put the profile. Find out the same thing. That's why I put here. Rho F by rho is at net for clear sky, and rho F by rho is at net. Net means sum of all those things. Subtracting for all sky minus clear sky, I will be getting the cloud radiative force. If I put all sky minus all sky means cloudy aerosol sky and clear sky, I get aerosol radiative force. So this is how radiation transfer is being. It's a book called the LEAV, Atmospheric Radiation Transfer. It's not a very complex book. It's a simple book. Okay, it's worth reading. It's called Atmospheric Radiation. Atmospheric Radiation. By LIOU. He's a very well-known scientist. He writes even papers. Not very old papers, classical papers. So the radiative heating rate for clouds or aerosol, basic principle is what I told. You already have the profile of it. I slab it into fine things, and then find out how much is the upwelling radiation and downwelling radiation, which I can do through radiation transfer. I can. If how much is the flux that is coming down, we already know Boucher-Lambert's law. That will tell you I is equal to I0 e power minus tau for each dz. Now for clear sky, cloudy, accumulated radiation. If I know this much is the radiation that is accumulated within DF, that DF is short wave up, short wave down, sum. Long wave up, long wave down, sum. And same thing here. All the four components added, I get DF, that's the graph. DF by D, because there's no point in taking this much and then saying DF. So DF has to be divided by the distance over which you are doing. Because over huge distance, obviously accumulation will be larger. There's no point in telling that heating rate is very big. That will normalize it. And then heating rate. This is now these days at least the minimum thing that is required for a paper. The requirement of aerosol optical thickness gone. Now everybody knows what is aerosol. The next step was we all used to do aerosol radiation transfer and then find out cooling rate, heating rate. This is also 20 years old problem. Now most of the papers already has, how much is cooling warming. Now what people require is this, find out how much is the heating. Because it has a meaning. I'll tell you one of the meanings. I put this profile. The heating rate also will show something like this. Now my axis is heating rate. It will also show, I am putting a relative scale. It will also show something like this. There's a problem here. This heating rate will add to my existing temperature. And effective temperature becomes, actually earlier temperature was like this. And the new temperature will become something like this. And here a kink has come. Correct? Yesterday we discussed temperature increasing, stable, but the potential temperatures will be huge. Nothing will go up from here. Means if there is an aerosol that is getting trapped there, it can make its own home. Aerosol accumulation can take place because There was an aerosol that was produced, a set of aerosols through a burning or something. Now it went up. It went up, solar radiation got absorbed there. It enhanced the stability of the atmosphere. More aerosol will be getting accumulated here, otherwise it would have gone further up. See the implication of it. There's a paper by Suresh Babu, SPL. Aerosols making their own home. See what he did is he did balloon experiment over Hyderabad and high altitude balloon experiment, ethylometer and so ethylometer detected, there's a hovering altitude for the spacecraft, aircrafts. Before landing, they all will be going around. And multiple times they may go around because landing may not be perfect. So there is a net accumulation of black carbon here. I think he found it around 8 kilometers. When he did this calculation, then there can be stability change and it can actually produce this one. So basically it can affect the outer layer because here also temperature taken and elevated it will make it so. So there are a lot of implications of what we do. And for cloud, it is huge. It is much larger than aerosol. That's why we'll come to aerosol, cloud radiative heating and all very soon. But all what we did is the same thing. And how do you know this radiation transfer? You cannot do with an analytical, I is equal to I0 equal to -2 because it is all spectral. So you use an engine. Engine means a driver, a software for doing this calculation. Ideal thing can be SP dot. SP dot is not the actual thing. It is DISOT, discrete ordinate radiation transfer. DISOT. DISOT is a code. Don't touch it. It's an engine. That's why it is called an engine. Don't touch it. Engine needs driving. So the front end is the driver. That is SP dot. DISOT is the code. That is the code. That is the engine. There's a front end that defines what is the basic parameter, what is the aerosol profile, what is the cloud profile, all those things that you can define. But inside stuff you don't touch because the moment you touch it, it will go. Because there are two people, Warren Wiscombe and Stemness. You just search their profile. They started this DISOT code with a project, it is another project, with 6 months. Warren Wiscombe is the first in radiation transfer. And Stemness has written a book on radiation transfer. This you can search that. Stemness. These two people sat together for 6 months as a project. It took 3 years for them to complete DISOT. Okay, so that is the level. At the top of that, they have written, don't do any modification to this. You are not responsible. I used it because for my satellite remote sensing, I used the DISOT. But I wrote my own front end because satellite remote sensing, SP dot will not do that. So I have to have my own front end. So SP dot is another thing which will give you it is more versatile. For my case, I was looking for AVHR or this man. I can define it. SP dot is good. SP dot it's a more versatile thing. Like you can define atmosphere there. You can define water vapor there. You can define what is the profile of the water vapor. What is the profile of the ozone? What is the concentration of the ozone? If you don't know the profile, they will assume the profile which is background profile. You can put aerosol there. You can put cloud there. You can remove cloud. You can put aerosol. Like that. But a lot of sensitivity experiments can be done. It is important that we handle, you people being researchers, this calculations anybody can do. But you should be equipped with certain new things, certain technologies. Like, AI, business ethics. In our area, we say you should be knowing some model. At least you should be able to run a model. But running a model simply plus P plus Q will not do. You should know how to prescribe the parameter for that model. For example, boundary layer or sea surface temperature or whatever, parameter, Q parameterization. And what you are telling is selecting those things. You are not doing any other thing. You are not meddling with the code. Okay, but that itself is a skill, and it is not very difficult. With 1 month, you can master it. As far as I'm not telling modifying the code, running the code, and using the code. It's not a very big deal. Same is the case with the SB dot. You should know SB dot is much simpler. You can learn it in 1 week's time, and there is a good help. There is a document on what are all the. And if you read the maybe first couple of chapters of Leave and go for SP dot, you already have the full concept. This directionality matters. This figure may appear very simple. This coming down. This coming doesn't like me. Coming down is one sign, going up is another sign. Unless proper sign is put, you will get double hitting rate. You understand? Going up is lost, coming in is gain. So sign conventions, simple things, but sign conventions are to be followed.
So there's a contradiction with aerosol, some create cooling effect and some
Correct.
create warming effects. How
It's a very simple thing. Aerosol will never cause warming at the surface. I is equal to I0 e power minus tau. It will never enhance I. It will always decrease I. Because at the surface, radiation is coming from there. All the places where it is absorbing or scattering, it will be lost. Right at the surface, radiation will always be decreased. Solar radiation, I am talking solar radiation, will always be decreased till the surface. So aerosol will always cause a cooling at the surface. It will never cause warming at the surface. But just the layer above, maybe 100 meters above, that place, it absorbs the radiation or it can scatter. If it is purely scattering, it will not cause any warming. It is scattered out. If it is absorbing, dou F by dou Z is positive, it will cause a heating. So heating or cooling of the aerosol is in the atmosphere. At the surface, it will be always cooling. Now let me go one more step and correct it. Atmosphere will never cause even a cooling at the layer in which aerosol reside, but some, for example, I have an aerosol layer. The region below that aerosol layer can be cooled, but that aerosol layer will always be, it will not be cooled, it will be only warm. You understand what I am saying? Because the amount of radiation that get absorbed there. But as it passes through, it may still get absorbed because still some radiation is there. But most of the radiation got absorbed at the top layer. So it can get cooled. So atmosphere can have both cooling or warming depending on the aerosol profile. If there is a huge, a simple thing, why dinosaurs were extinct? Dinosaurs were extinct because there was a huge meteor that fell. There is a record for all these things, very record. Huge amount of dust plumes have gone into the atmosphere, reached the stratosphere, where they resided for several years. Even a volcanic eruption will cause almost 2 years, 3 years is the residence time of the stratosphere. So huge amount of dust when it goes, it resided in the atmosphere, caused the surface cooling. So temperature went down by around 20 degrees. All these things are having records. Meteor fall, there is a record. Temperature record, there is a record. All those things are recorded. 63 million years before. And the largest species, their results also got extinct around that. Smaller species survived because they require, those who require huge energy, sensitivity is very high, they got extinct. Other species are alive. So this is the effect of aerosol. If an aerosol layer, huge layer of aerosol is there, the beneath region will not only at surface, even the atmosphere will get cooled. Because there is no solar radiation that is passing through this, because most solar radiation comes from the stratosphere itself. Okay, there's an area called there's an area called geoengineering, where one of the methods by which they are speculating how to regulate the temperature of the increased earth, warming, put spheres there. So that amount of radiation that is coming is also equivalent to also there. Yeah, you are asking.
You told some another aspect of climate change is take the concrete, take the total sum of Earth and atmosphere, its temperature is 288 Kelvin, just above. Can you explain?
Actually, go there. This is temperature, this is height. My 255 Kelvin has come now at, this is a temperature profile. This is 300 Kelvin. This is 5 kilometer is 273. So 255 has come 7 kilometers. Today, the globe get warm. Still, as far as going back to space, there can be 255, it can be lower, it can be higher. Usually what it happens is 280, it will become something else. So where I will have, now I use that equation, I will have an effective temperature. That effective temperature, now the atmospheric temperature also got perturbed now. by something. Where is that effective temperature? Now,
Sir, maybe the lapse rate will come in picture.
that's what I'm saying. Lapse rate means actual temperature itself.
Yes.
Lower temperature, lower atmosphere may be warming faster, upper atmosphere may be warming slower. So where is my new equilibrium, that effective temperature difference that has come? Is the one that I was telling them. This picture I put for radiation transfer, not for satellite. I told you that thermal infrared 10 to 12 micrometer. No, just come. No problem. Yeah, I think it's okay. Okay, this is Australia. Are you able to see here? Dark, ocean, bright, land. Because temperature is high. What is the time? The time there is Indian Standard Time. Indian Standard Time evening. 2200 approximately 9 o'clock in the evening. Australia is still night, but still the Australian surface temperature is higher. Okay, and at that time, the Arabia is almost in the evening on the western side, very black, correct? Now even Madagascar island you can see slightly brighter. So the ocean and the land are very clearly discernible because the temperature is different. That wavelength band is 10.5 to 11.5 because what is that written at the top? Thermal infrared at 10.8 micrometer band. You see the right side band. Right side band is water vapor band at 6.8 micrometer inside 3D. It never sees the surface because the radiation that is actually surface is emitting, but surface was not able, that radiation was not able to penetrate through the cloud because cloud is completely absorbed it. And all what you see is an entirely different picture compared to this. There are some similarities, complete differences. The similarity is this. Wherever you have very deep convection, it is. So that deep convective clusters are exactly the same. Low altitude cloud, this is Mascarenhas high. This is the Mascarenhas, Madagascar. They are having low altitude cloud because the brightness of it is very low there. Their altitude is only 2 kilometers. Because it cannot penetrate below around 4 or 5 kilometers. It can see only above. But above, what it sees, this fellow doesn't see. See, it is all hazy here. Here, nothing. Actually, because there is water vapor that is getting transported from this deep convection and then going straight. That is absorbing. This fellow is not able to see to that extent, but this fellow can see because it is highly sensitive to water vapor absorption. Actually, we derived one more. We went on step ahead. We can find out whether it is cloud or means thin cirrus, superficial cirrus, or water vapor. We can discriminate because cirrus both are upper altitude cloud. So some signature will come in both, and depending on the contrast in these two volumes, you can find out whether it is cirrus or not. I'm not going into those details. But what I'm trying to tell you is this is the practical side of the absorption cross sections that we study. Water vapor absorption cross section. Practically, you can find out what is the surface temperature here, whereas you cannot do it here. Instead, you can study upper tropospheric water vapor, humidity, or thin cirrus clouds, which you cannot see there. But both require application of radiation transfer, band radiation transfer. This we discussed yesterday. Why I kept it here? Because now we are going for clouds. For clouds, I thought this is an important. I will not go again more into what we discussed already. All what I want to tell here is, yesterday we were telling that only 47 is coming here, 23 is absorbed. This absorption, there is good fraction that is coming from the clouds. While going out, 116 is emitted, 104 is absorbed by the cloud. Latent heating, significant amount of absorption comes from the cloud. This absorption significant amount come from clouds. So in the whole budgeting, whether there's a net ready cooling here, net ready warming here, clouds play the most predominant. All what I want to tell from this figure is that. If this figure yesterday we explained, otherwise we will take another hour. We will don't want to do late. There is a much bigger dimension to this. That is what I have written there. You just assume. Now we put what are the greenhouse gases? Carbon dioxide, water vapor, methane. I remove all water vapor. I put only carbon dioxide. I will get a temperature change of maybe 20 degrees, 10 degrees centigrade. The 255 which we calculated, and the 10 may come from carbon dioxide. I remove carbon dioxide, I put water vapor. I may get something like 50. Okay. Now I put water vapor and carbon dioxide, 10 from carbon dioxide, 15 from water vapor, which is 25. But I will get 30. You understood the problem? When I mix them, the effect of each one of them get amplified because now it has more IR radiation because water vapor emits, absorbs and emits also. Now carbon dioxide gets more molecules, more radiation of IR to be absorbed. You understood or not? Carbon dioxide is absorbing and emitting. Water vapor is also absorbing and emitting. So availability of infrared radiation becomes larger because of this species. What it does is it will amplify the effect of greenhouse effect. So if I put water vapor alone, if I put carbon dioxide alone, if I sum up these two, it will not be same as if I put carbon dioxide and water vapor together. That is why it is said that water vapor amplifies the effect of carbon dioxide. So water vapor is the largest greenhouse gas. But actually speaking, if you take in terms of magnitude, carbon dioxide is very high. But water vapor is such a variable thing. So it is carbon dioxide is not added. We cannot say that carbon dioxide is added because carbon dioxide is added, but global mean value is remain the same. Water vapor is changing. Water vapor is drastically changing. Over Arabia, it's very small. Sahara, nothing. Or Indian region, you have huge values. Or tropics, you have huge values. So that amplifies the effect of carbon dioxide. That's what is written here. That is why we say water vapor is the largest greenhouse gas. Otherwise, per se it is not so. We know what is the important. Now we are going to clouds actually from radiation. We are coming to clouds. Maybe up to 1 o'clock we can go. I have no problem. No, the question is you feel sleepy or we can go. No, but I don't know. See, there is a problem. The movie, now I have traveled. I cannot get out. So there is no problem. I can stop anywhere, anytime. But I have one advantage. That advantage is while speaking, I get energy. While listening, I lose my energy. So I cannot listen, but I can talk. There's no problem. Because listening is a problem. It consumes energy because your brain requires a lot of energy. You know that. It requires energy for absorption. Anyway, these are all very simple things. I can proceed to 1 o'clock maybe. Your lunch time is 1 o'clock, 12:30. First thing is clouds play a major role in the radiation transfer. Because without clouds, I told you, albedo of the cloud, most of the thing is contributed by clouds rather than. There's a huge role in hydrological cycle and redistribution of water. See, yesterday we were discussing. Latent heat is taken from here, not at the above, it is dumped. It is dumped maybe at Russia. Because this water vapor can go all around, because 14 days lifetime can be there in the water. It go to Russia and then condense. It can, in principle. Thermodynamics of the troposphere and stratosphere is fully governed by water vapor and carbon dioxide. Okay. Vertical coupling of the atmosphere. This is one thing which we have to be very careful about. Vertical coupling of the atmosphere means, you just imagine this. I did not put a slide here. There's a mechanism called conditional stability of second kind. Yesterday we talked about stability of the atmosphere. Theta increases stable, decreases unstable. This is called the first kind. If there is a instability, that is instability of first kind. Conditional instability. Condition is what? Theta increases or theta decreases. There's a next conditional stability, that is conditional stability of second kind. This is massive. This is the same thing. Now you are having an instability, this fellow has gone up. Now water vapor is condensed. Latent heat is liberated. Heat is changed. Pressure decreases. Further, the fellow goes up because low pressure is deeper. The fellow goes up, no more fellows goes up, more condensation occur, more heating, further deepening of the pressure, it will further accumulate more. So a convection will keep on intensified by itself once a seed is there. You provide the seed, remaining by itself it will make because it like an engine. It intensifies. This is how cyclone is getting intensified. Cyclone acts as a low. We say low pressure. That's a seed. A low pressure becomes depression, deep depression, cyclone, very severe cyclone, depending on if it is in warm ocean. And upper level divergence should be there and wind shear should be minimal. If this much conditions are met, it will become a super cyclone, no doubt about it. But most of the time what happens is it will have a sea travel. For example, Indian Ocean it is coming and Bay of Bengal, it reaches the land and then it cannot further intensify. Second is there can be wind shear, very high wind shear. Wind shear will not support because this fellow has to go up and then make all what we are telling. So if huge wind shear is there, it will not be able to reach up to that. Okay. And upper level divergence has to be very high because then only low level convergence will be there. If people are keep on entering and people are not leaving, more people cannot enter. So there has to be an exit. That exit also should be equally good as entrance. So upper level divergence will enable low level convergence. So this is called the conditional stability of second kind. My father is a farmer. So he has, we all view things in very primitive fashion. My father he used to say, once you become a thief, you start. Then what happened is you are branded. Now you are branded, you become a professional thief. It's a positive feedback, correct? So once we cause a mistake, we are branded, and that branding will cause you to accelerate that mistake. Same is happening here. You have the water vapor condensation take place because of instability. That is conditional stability of first kind. This fellow was going up. Then onwards, if you have sufficient water vapor at the surface, evaporation, that is warm sea, this fellow will sustain by itself. That conditional stability of second kind is required for any massive system to develop. Otherwise, it will be maybe to cumulus it can form, or maybe cumulus congestus. That's all. If you want to have a cumulonimbus cloud, even deep convective cloud, you require SISC. Okay. And you can also generate gravity. I mean, atmosphere goes from these things. Gravity was? Gravity was, right? Gravity was, Gravity means, atmosphere. This is gravity. It's actually acoustic gravity. Only thing is, you will not be able to, all the spectrum, you are not able to see. Part of the thing is still there reverberating in the atmosphere. Because atmosphere cannot support all the frequencies that yesterday we discussed, Weisner frequency. All what you heard is having a high frequency. That fellow will not be reverberating around. There is some frequency that is there which can support, it will go. So this is thunderstorm. Thunderstorm can produce this. Much of the gravity waves are produced by thunderstorms. Much of the gravity waves are produced by thunderstorms. So these clouds can generate these kind of things. Cloud latent heating can also generate planetary waves. We will come to that. They are actually regulators of climate change through cloud feedback and role in deciding lifetime of atmospheric species, for example, water vapor. I mean, the bigger part, aerosol. Aerosol resistance time in the atmosphere is decided by water vapor. If more clouds are there, clouds take it, and then if it precipitate, it is washed out. Or when rain is coming, it is rained out. So, water vapor, water and clouds decide lifetime of aerosol. And aerosols can grow if water vapor is. So you see, it provides a feedback. It can be positive or negative. It will cycle. And in fact, some of the water soluble species also can be removed. For example, sulfur dioxide in the atmosphere can be removed. You know why pH value of rainwater is acidic? It's because carbon dioxide is there and becomes carbonic acid. So you have an acidic thing invariably here in the pH of the rainfall. It will not be base, it will be acidic, minuscule. But if you have the first rain, it will be more acidic because you have sulfur dioxide, so many species. So it acts as a water soluble, chemicals will be removed. That's what I mean. And that's why after rain, sky becomes. because aerosols, all those things are there. And it has a role in atmospheric chemistry and atmospheric electricity. Clouds are the primary, agents of atmospheric electricity. And this atmospheric electricity and then pertains to ionosphere. There is a global electrical circuit. It links to ionosphere. Clouds interact with the atmosphere, impact our radiation budget, energy budget, and is one of the biggest uncertainties in climate change. Climate change actually, almost none of the models are able to reproduce cirrus clouds exactly. And similar is the case with marine stratocumulus. If you tune your model for marine stratocumulus or cirrus, other clouds goes. So this is a complexity. Tropical clouds are of most importance. The reason being, this cloud is the tallest cloud in the world because your tropopause is 17 kilometers. So here the clouds can go up to 17 kilometers. That is the coldest cloud top in the earth compared to polar clouds or mid-Atlantic. So the radiative forcing will be completely different. Obviously, redistribution of energy. Most importantly, that will cause stratosphere-troposphere exchange because tropopause acts as a lid. But huge convection can even penetrate through the stratosphere. There can be a small bulge that is coming. Okay, that can enter. But normal stratosphere-troposphere exchange don't require this penetration. There's a loose boundary through which it will be penetrated. But it can accelerate. Deep convection can accelerate. So longer radiative forcing is this is a paper by Jeff Keel, Ramanathan. Jeff Keel. Ramanathan is a first fellow to do cloud radiative, effects study quantification. And then his PDF was there. His name is Jeff Keel. Jeff Keel has found that the short wave and longer radiative forcing at the top of atmosphere cancels. So at the top of atmosphere, there is no distinction between clouds or non-cloudy times. As far as cloud radiative effects are concerned, if you take individually, it is and averaged for day and night. Day and night, there will be change. So it is not that cloud doesn't have an effect. Cloud has huge effect. Net radiative forcing is zero at the top of atmosphere. This became a classical paper. Rajeev and Srinivasan brought in the next. Over the monsoon region, it is not so. Over the monsoon region, there's a net cooling at the top, minus negative radiative force. This paper appeared in Journal of Climate, Rajeev and Srinivasan. That's one of the most referred papers. Classic work. That is the effect of monsoon in completely changing the hypothesis that is put forward by Jeff Keel, which was accepted otherwise. That is the last statement. What do you want to study in clouds? Because when you are studying clouds, so many things you want to study. And all these things are relevant. And none of us will be addressing all of them. Maybe one or two of them is what we can address. So a potential list can be cloud size distribution. You are asking aerosol size distribution. Same way, cloud size distribution. What is R effective? Because drop is very small, it is not going to be split. And drop is very small, it is going to be more whitish. I told you, smaller particle will backscatter more. They appear more bright. So many problems. Cloud phase is a problem because still we do not know what is a fraction of the cloud which is in ice form or water form between 5 to 8 kilometers. Because 5 to 8 kilometers it can be in mixed phase. Water can exist even below 0 degrees centigrade, super cold. So even up to 8 kilometers, water can exist in super cold form. But above 5 kilometers, it is 0 degrees centigrade. It can be ice, but we do not know what is the fraction of ice versus water. There is large uncertainty. And we still are not able to, even today, we are not able to accurately measure how much is ice water content and liquid water content. Even CloudSat is not able to do it. It is an approximation. Water content, liquid water content, it is able to do better. Ice water content, there is an ambiguity. But still we use it also. But there is an ambiguity larger than liquid water content. Cloud optical properties is one of the things which is least known, especially even emissivity. And emissivity matters because that is the one which will be deciding on the temperature of the cloud. Cloud type is another. Actually, visually you can segregate clouds, but to have the cloud types discerned from the observations of radar or lidar, even imager, three-dimensional shape of the individual clouds and type evolution. This is called cloud size distribution. Next point is because clouds can be small, cloud can be big. What is the size distribution of the cloud? Not droplets. Cloud distribution, the size distribution of the clouds itself. Ramiroka has a paper on this. Cloud distribution. Ramanathan and Ramiroka. It's a very good. Cloud vertical distribution, like we are telling about heating rate, where it is, where it will move and all this. You require vertical distribution, spatial distribution, and life cycle of the cloud systems and lifetime of different cloud types. They're all hardly known. Why I am telling? We may think we know everything. You know the deep convection that produced in Bay of Bengal transports cirrus clouds to Arabia. And over Arabia, where you see that normally it is cloud free. That earlier figure itself shows that. See, in semi-transparent cirrus clouds reach up to Arabia, whereas here you don't see that. Left hand graph you don't see. Long range transport of cirrus that is produced from the deep convection or the Bay of Bengal through tropical easterly jet stream, it can reach up to that. Still, it is a research topic. My student has worked on this, and she has submitted a paper in Journal of Climate, not Journal of Climate Dynamics. Reviewer comments came. One of the most important points that they appreciated is this particular point. Like, we found out how much is the lifetime and spatial extent to which cirrus is getting produced and then transported. So this, even today, what I'm trying to tell you is, these are, we may think what to study in that. A lot of things, much of the things are unknown. All what we know is blah blah blah. Remaining is quantity, because we require quantitative numbers, which is unknown. Distribution of clouds in synoptic systems. When I say synoptic system, monsoon system. I'm going back to my earlier. I'll give you a problem for yours. One. You know, monsoon is a shallow convective system. Monsoon doesn't give you thunderstorm. It's a shallow convective system. Shallow means thickness is very low. It is confined to below around 2-3 kilometers or 5 kilometers. This is the Mascarenas cloud. System comes from here and enters into the Arabian Sea. Mascarenas cloud, let it be there. Over this place onwards, you have cloud city. And no deep convection comes even up to here. But deep convection comes here. So south of Bombay, it is not much deep convection. North of Bombay, you have monsoon trough convection. This region is deep convection. This region is shallow convection. Isolatedly, this region can become convection. But that is isolated. It's not very big. That's why monsoon time you will not get thunderstorm. Very rarely you may get one or two, but otherwise. Now I am giving a question which nobody has done so far. What is the vertical distance? And this was inferred by O.P. Rao. There's a book. It's not a book. It's called a meteorological model. You have it. If you don't, I have a copy. A copy. You know, 1976. None of these kind of observations exist. Not even this satellite exists. Like Kalidasa, he derived altitude profile of clouds, altitude profile of moisture, tropical easterly jet stream, tidal wave. We have everything. Nothing more than what O.P. Rao told we have done so far. We did it a little bit more pictorially and more information. But fundamental knowledge, O.P. Rao, 1976. He said, vertical development of clouds will be very shallow here, very shallow here, very shallow here, and will be very deep. Now my question is, he told you shallow. How shallow? And as you evolve, what is the way in which vertical distribution of clouds vary? I am proposing that here it will be of the order of 2.3 kilometers tall. 2.3 kilometers. All these places, and here most of them will be 2.5 to 3. And from here to here there will be a systematic increase. And here occasionally it will go to even 8 or 9 or 10 or 12. But there will be a distribution. Most of them will be below 5 kilometers. So here almost 100% time below 2 kilometers, 3 kilometers. Here 100%, I mean 70% time below 3 kilometers. And sometimes up to 5. Here up to, I mean over the Indian region, majority of time below 5 kilometers. But maybe 30% of the time it can go above. So there's a deep convection that is fixed. There's a possibility. And that is, OLR also shows that. So there's a possibility. Here onwards, our time, from below to top, everything exists. This is not so problem. Right. Conjecture. Can you prove it? Clouds are data. Take it. Do the analysis. You'll get this. You'll get a good paper. Okay. So what I'm telling is, a lot of things are not known. It's all hypothesized, but you have observations. You have to look at it. And 1 or 2 satellite paths will not do. You have to have 18 years of data analyzed together. Otherwise, nobody is going to accept it. Clouds and radiation, we already told. Clouds and precipitation, we did not talk about that so far. And cloud formation and triggering of meteorology. For example, what is the relationship between, clouds are formed only over warm ocean. Where? What is the SST minimum required? And how does cloud deep convection vary with SST? That itself is a topic by itself. That's only one parameter. Stability is another. SST gradient is another. So many parameters. And cloud feedback, that is the least known thing so far. Cloud feedback means cloud has formed now. Cloud will start cooling or warming, and that will further modulate its circulation. This is any one of these aspects, if you address, it becomes a thing. So it is such a vast area as far as cloud physics is concerned. I think 1 o'clock we can leave. Actually, tomorrow we can. But only thing is, I reached only half of what I wanted to do today. These are all very interesting aspects. Okay, there's polar curve, and this is what you might have already seen. Nucleation, and the physics of this nucleation is what I will show you. This is picture. This is the physics of it. This is the physics of it. And then I wanted to talk a little bit on gem circulation, but somebody has talked about gem circulation. Okay, even if somebody is talking, full, I have no problem, because what I am going to talk is a slightly different one. Because I am going to, there are certain features hitherto not known, but that can be known from cloud observations. Because where is the vertical velocity measured? Nowhere, except in 1 or 2 radars here. Vertical velocity is inferred. Whereas over the whole globe, you have cloud distribution. Cloud distribution can be used to infer circulation. And then when you find that there are certain circulation features are not understood, not discerned so far, like pool of independent cloudiness. Now that we made as a paper, Anish. And there is another that now Ashwati has done. That is the Western, Pacific. That's the biggest ascending limb of Pakistan. We'll come to that. So far, it is told that is the biggest ascending limb and a continuous, massive. It is true, but actually, it is a broken limb. There is a central portion that splits into Eastern Pacific and Southern Pacific, Western Pacific and Southern Pacific. There's a clear gap region come. It's from Philippines area downwards. Very clear. So those kind of things come from cloud vertical distribution, because you have a very lacuna in cloud, which was not there in other places. So that part I want to cover. Unless I do little bit on this, I will not be able to do that.
Inferring and measuring are
different. Inferring and measuring are. This is a very important thing. You have 3 terms in science: observation, estimation, and inference. You have to discriminate these two. Observation is an observation. I saw that. Clouds, I saw that. Radiative heating, I estimated. That radiative heating change in circulation, I inferred. That's not even an estimate, it's an inference. That's what you do. There's a fundamental difference between observations, estimation, and inference. This we should be very clear. Okay. Nobody will tell you these things. Because I also was not told by, I did not read this from any book. This question is very true. So when it is inferred, you have to write it is inferred. So what she is referring to, the splitting of the Western Pacific Wakasa, is not an observation. It's an inference based on the observation of vertical distribution. But that inference is strong because you have further evidence year to year and all those kind of things. That is it. This is what I was telling. Actually, this is that Pacific, that big cell. It appears as a single cell in all figures which is here. All figures will show this is massive. But actually, it is splitting from somewhere here. So one limb will be here, other will be here, and this is weaker. As an annual cycle, these limbs both expand and then join together in winter. But in summer, especially October, November, December, they clear this implication. This region becomes very dry, and there is large number of forest, large amount of forest and peat. Peat means after your agriculture thing, the things that you cut, and then that they burn. So that is a natural process. They do that as a farmers, but that will trigger forest fires. So huge forest fires occur here during August, September, October every year. And El Nino years that becomes very massive that the smoke come up to here. We have detected. We have a paper the smoke coming from here. But every year it happens, but that may be small. That is the time when the splitting is there. You can see from here. Anyway, those things we'll cover tomorrow if we have time. Actually, this is what I wanted to put it down. This is germ circulation, but it is an inferred germ circulation. It is simply movement of clouds stitched as a time series. So that it will give you ITCC, it will give you mesocycle conductive systems, it will give you descending limb of Walker cell, Hartley cell, it will give you the Walker and Hartley cells, all those things. This we will discuss tomorrow. And then this I just wanted only for information. This is the cloud distribution classification. And here I wanted to end this, and tomorrow I wanted to put something, but only 50% is. Maybe by tomorrow we'll cover a little bit more. I don't mind spending time, but at the same time, I don't want you people to waste your time. I can even come early, actually 10 o'clock, because we in BSSC, we start with the 8:45. We are tuned for that. Your time is, I think, 10 o'clock, is it?